as I said, fifth and sixth assignments are entirely based on this. Okay, and this time the assignments will be for a group of 2 members, and the 2 members shall randomly be picked up by Dr. Javed. Okay, all right. These 2 members incidentally could be the 2 members who were in the earlier batch, or maybe from the other batches also. Okay, so now what is a tree? Tree is a subset of the graph G. G is a set of vertices and set of edges, you know that, and tree is a subset of graph such that the set of vertices shall remain the same. The set of vertices shall remain the same, but set of edges will be only n minus 1 out of E edges. Okay, it shall be just n minus 1 out of E edges, and they should satisfy certain properties. Okay, therefore tree is a subset of edges, and in general tree is a subset of a graph. So it is a connected graph. Tree is a connected graph without any circuits. So in graph there may be circuits, but in tree there should not be any circuits. Graph is a connected graph. Tree should also remain a connected graph. So the definition is tree is a connected graph without any circuits. Please follow these definitions carefully, because each definition should become an algorithm to construct a tree from the graph. All right. So another definition, a tree contains one and only one path between every pair of vertices. All right. So as I said, all vertices shall remain same in trees, and there must exist one and only one path between every pair of vertices. There should not be, in a graph there can be more than one path between a given pair of vertices, but in a tree it should be so chosen that there must be one and only one path between every pair of vertices. So tree is a connected graph with just n minus 1 edges. Tree is just connected and should be n minus 1 edges. See, even in the first definition it is a connected graph, but there it has not been told as n minus 1 edges. It is said as without any circuits. Is that all right? And second definition contains one and only one path. One and only one path. So path shows the connectivity. So it is connected. But it does not tell n minus 1 edges. Okay. Now, tree is minimally connected. I have got to define what is minimally connected. A graph is said to be minimally connected with reference to a particular edge, provided that edge, if removed, disconnects the graph. So you consider a edge, you just remove that edge. When you remove that edge, the graph gets disconnected. Then it is called minimally connected with respect to that edge. So tree is minimally connected with respect to every edge. You remove any edge in the tree, the tree gets disconnected. So T minus E is a disconnected graph. The very first interesting question of logical deduction or proving is to show that all these statements are equivalent. All of them are equivalent statements. This statement is equivalent to this statement. This statement is equivalent to this statement. This statement is equivalent to this statement. So you have got to logically prove that. So that itself could be one interesting part of work for you. Okay. So these are the definitions of tree. Now we should make use of these definitions to come out with the algorithm. Before that, we shall see a tree with minimum number of pendant vertices. Naturally, a tree is a connected graph, but it should have pendant vertices. What is a tree with minimum number of pendant vertices? So the minimum number of pendant vertices will be 2. See, this is one pendant vertex with degree 2. This is another pendant vertex of degree 2. And all these vertices here are of degree 2 each. They are all degree 2 each. This is one pendant vertex. This is another pendant vertex. This is Hamiltonian tree. You know, you recall we had defined a Hamiltonian circuit. Hamiltonian circuit is the one which goes through all vertices once and only once. Even here, it goes through all vertices once and only once. but it does not make a circuit because this vertex is not connected to this vertex. Therefore, it is an open Hamiltonian path. And this Hamiltonian path, since goes through all vertices, it is a tree also. It is a Hamiltonian tree. So it has got, this is a example of a tree with minimum number of pendant vertices. So minimum two vertices have got to be, two pendant vertices have got to be there in a tree. Let us see which is a tree with maximum number of pendant vertices. So maximum number of pendant vertices is a starburst. You can see that this is a tree. So this tree is connected, this vertex is connected to every other vertex. Every other, of course, every vertex is connected to every other vertex, but it is through this particular vertex. All right. So a tree with maximum number of pendant vertices, and n minus 1 vertices are pendant vertices. Only one vertex is the centrally located vertex, which has got the connectivity of all of them. So this is starburst. So starburst is the tree with maximum number of pendant vertices. Hamiltonian tree is the tree with the minimum number of pendant vertices. So let us see, let us prove why minimum number of pendant vertices should be 2, why maximum number of pendant vertices has got to be n minus 1. Let us prove that. We know that sigma degree in any graph, or a tree being a graph, should be equal to twice the number of edges, and you know the number of edges is n minus 1 and twice n minus 1. You know, you recall the definition n minus 1, 2 times n minus 1. So that has got to be there. Now let us see how I can split this 2 into n minus 1. You take up this graph, the Hamiltonian tree graph. There are 2 vertices of degree 1, 2 vertices of degree 1, and all the remaining, how many remaining are there? N minus 2. N minus 2 vertices are of degree 2. They are of degree 2. The summation should be equal to 2 into n minus 1. So I can split 2 into n minus 1 as 1. Okay. So n minus 1 vertices, okay, of degree 1 plus 1 into n minus 1. I mean, this is for maximum. Please look it here. I can do it as n minus 1, n minus 1, one vertex of degree n minus 1, and n minus 1 vertices of degree 1 each. N minus 1 vertices of degree 1 each. This is for maximum. So n minus 1 vertices of degree 1 each plus 1 vertex of degree n minus 1. This is for maximum. Okay, that is a starburst. Now, as far as minimum is concerned, that is equal to 2 into n minus 1. As far as minimum is concerned, 2 vertices of degree 1 and remaining n minus 2 vertices of degree 2. Let us see how that is possible. So 2 into n minus 1, I can write it as 2n minus 2, 2n minus 2. And that can be rewritten as 2 plus 2n minus 4. See, this is all that I have done is added plus 2 and subtracted plus 2 and minus 2. Add and subtract 2. So when I add and subtract 2, that becomes 2 plus 2n minus 4, which is 2 plus, in 2n minus 4, remove 2 common, which is 2 into n minus 2, which tells that there are 2 vertices of degree 1, and that contributes to 2, and there are n minus 2 vertices of degree 2. So this will be 2 into 1 plus n minus 2 into 2. In other words, for minimum, there are 2 vertices of degree 1 and n minus 2 vertices of degree 2 each. All right. Okay. Now, let us extract the algorithms. Let us formulate the algorithms to extract a tree. These are all transforming the definitions of a tree into algorithm. Listen to them carefully. So now, because it is a tree, you know that tree is a minimally connected graph. In other words, there is no scope for parallel edges. There is no scope for self loops. So the very first work is, given a graph, just identify the presence of all parallel edges and self loops. Okay. Therefore, because the parallel edges cause circuits, self loops definitely cause circuits. Therefore, remove all parallel edges and remove self loops. That is the first pre-processing that we have got to do. So if there is a general graph given to you, convert it to a simple graph. That is the first work. So general connected graph is connected into simple connected graph. Then, which simply means if it is incidence matrix, general incidence matrix given, convert it into a simple incidence matrix. If it is a general matrix, adjacency matrix given, convert it to a simple adjacency matrix. Then the next question is, starting from this matrix or starting from this matrix, how to obtain this tree, which is of n minus 1 edges, whereas here it has got e edges. Here also it has got e edges. All right, how to get that? So that is how to transform this matrix, A matrix, which is n cross E, into a matrix of n cross n minus 1. All right, how to transform this matrix into still a n cross n matrix, but number of ones have got to be removed so that there shall be only n minus 1 ones, n minus 1 ones. So this is what is the job that we have got to do. So ultimately the job is transform a matrix from here to here, transform the matrix from this point, this starting point, to this starting point. That's all. Okay. All right. A tree is connected. This is one of the definition. A tree is connected with only n minus 1 edges. Note that definition. So a tree is connected with only n minus 1 edges. Therefore, the algorithm should be to make a choice of n minus 1 edges out of the e edges present in the graph, such that the connectivity is maintained. In other words, all vertices remain connected. Recall, that was the very one of the first assignment that you did. How to check the connectivity in a graph, whether the graph is connected or not. So that is the algorithm that you have got to again re-employ here to check whether the connectivity is maintained or not. Therefore, it is a way of choosing n minus 1 edges out of e edges, So it is very simple. Choose n minus 1, a subset of n minus 1 edges out of e edges, and then check whether the connectivity is maintained or not. Therefore, it is a two-stage algorithm. So the algorithm is retain only n minus 1 edges at a time. Hence, accordingly, update A matrix or X matrix, check if the resultant matrix is connected or not. If it is connected, it is a tree. If it is not connected, it is not a tree. That's all. Okay. Therefore, this algorithm is a non-polynomial type of algorithm because it has got two stages. Number one, obtain the first subgraph of n minus 1 edges and check whether the subgraph is a tree or not. So two stages. First is just choosing randomly. Second one is checking for the connectivity. If the connectivity is established, then it is a tree. If the connectivity is not established, then it is not a tree. Therefore, it is a combinatorial problem of choosing n minus 1 edges out of e edges. Therefore, it is a factorial type of algorithm, but nevertheless, it is worth trying it. And this is the simple, transformation of the algorithm into a performing algorithm. All right. Okay. So now, this algorithm, surely this method can give rise to all possible trees, because you are trying to get all different combinations of n minus 1 edges. Some of them may not be acceptable, some of them will become acceptable. All those which become acceptable will yield all possible trees. So it will give all possible trees, number one. Number two, a tree connects all n vertices. In other words, it is said to go through, it is said to connect through, it is said to span through all n vertices. Therefore, a tree is called a spanning tree. It is called a spanning tree. All right. If the edges are weighted, then to get the minimum weighted spanning tree is the important question, which is MS, the minimum spanning tree. Without so much of details, you have already done it in your algorithms class, minimum spanning tree. So recall and include into your pages the two algorithms that you had used, particularly in the weighted graph to get the minimum spanning tree. The two algorithms that you had learned were Kruskals algorithm and Prim's algorithm. Now there could be questions like, why Prim's algorithm is called most efficient algorithm? These are some of the questions. And Kruskals algorithm depends upon the edge sequencing. Prim's algorithm depends upon absorbing one by one. All right. Anyhow, I may not find time to go through these two algorithms because you've already learned these two algorithms. Okay. So now let us take up another definition. What is the other definition? A connected graph in which no edge can be removed without disconnecting the graph. You know, it is, you remember that it is minimally connected, some definition. So it is a minimally connected graph. So now what is the algorithm? Try to remove an edge, and upon removing the edge, if the graph becomes disconnected, then it is not going to result in a tree. So that edge has got to be present in the tree. If that edge does not, if the removal of that edge does not disconnect the gap, then remove that edge. Okay. If upon removing the edge, if the gap still continues to remain connected, then better remove that edge. Like that, you go on removing the edges. So this is not choosing n-1 edges. This is removing one edge at a time. Okay. So algorithm is remove an edge. Check if the resultant gap is still connected. If connectivity is broken, bring back that edge. Otherwise, confirm the removal of that edge and repeat it until just n-1 edges are left out. Because after that, any edge which is removed shall just destroy the connectivity. So that's an interesting algorithm. But this algorithm will not generate all possible trees. It will generate one particular tree, and it also depends upon the sequence in which you consider the edges for removal, or the type of data structure that you employ, and the type of scanning through the data set that you would do decides the type of tree that you are going to generate. So it depends upon the sequence of edges opted for removal operation. So how many edges you have got to remove? E minus n-1 edges have got to be removed. So you have got to, in general, you have got to try over all edges. It is an order of E algorithm, and it is order of n square in case of a complete graph, because E maximum is n into n-1 by 2. That's order of n square. So you should try removing every edge once at a time, and then bring back that edge or remove that edge. Bring back that edge and remove that edge. Therefore, in the worst case, you should try for all E edges, and E is of order of n square in case of a complete graph. This is the worst case. But this will not give all possible trees. This will give one of the trees, one possible configuration. Okay. All right. Now, another definition is a circuitless connected graph. A circuitless connected graph is a tree. So what are the things that you require? Either a matrix or an X matrix, and also construct a B matrix, because B matrix gives the circuit matrix of a graph. All circuits are present in B matrix. B stands for circuit matrix, you recall that. And it was your assignment also previous time. So now all that you have got to do is identify the circuit present in a graph. Remove that circuit. How can a circuit be broken? Remove any edge in the circuit, then the circuit is broken. Just removing one edge in the circuit, still all vertices in the circuit remain connected. They will not get disconnected, but the circuit is broken. All that you have got to do is break a circuit at a time. Therefore, that is the algorithm. Identify a circuit, remove an edge in that circuit. Intelligently identify an edge to be removed with the help of circuit matrix. This is a little advanced level. Don't worry about the bracket. At the initial time, all that you have got to do is identify a circuit and break that circuit. Okay. Identify a circuit, break a circuit. Okay. So when you break a circuit with an edge removed, there can be some other circuit getting formed. That you should be careful. All right. Update the circuit matrix. Update the A matrix. And repeat until G becomes circuitless. That's all. Just take the circuit, take the graph, make it circuitless. Identify a circuit, break a circuit. Identify a circuit, break a circuit, until the entire graph does not have any circuit, but still it should remain connected. This will also provide. This will also not provide all trees. It depends upon the sequence in which you consider the circuits and the choice of the edge that you break in the circuit. Therefore, it will not provide all the possible trees, but it will provide one tree. Okay. Now, Other algorithm, backtrack strategy. So this is depth first search to construct a tree. Let us see what is the algorithm. I have not given you the data structure, but I have given you the diagramic representation of a tree. Now I have got a diagramic representation of a graph. I have got to construct a tree out of that. And of course, in between stage is the data structure which you have got to work. You have got to work on data structure, but the algorithm is the following. Let us say I will start with vertex A. See, vertex A, you can see, let us go by depth first search method. This is depth first search. So I shall take edge x1, and edge x1 connects B. Edge x1 connects B. Now when I come to B, I can take x4. When I take x4, it will connect C. So now, so far, x1 and x4, so far the vertices are not repeated. So far, circuit is not formed. Therefore, I can go to the further depth. So maybe I go to the further depth. From C, I can choose the x2. But if I choose x2, I will come back to A. Now look at this data structure, the growing data structure. A, now it has again A is repeated. Although the edge is new, this is acceptable. Although the edge is new, this can be acceptable, but A is repeated. Therefore, you have got to backtrack. You have got to backtrack. So this cannot be possible. So from C, we will choose the alternate way. So now I choose from C, I can choose x4. Now the moment x4 is considered, this is x4 is repeated. Therefore, this cannot be possible at all. Much before I reach V, the user, the choice of x4 itself should tell you should backtrack. The real backtracking point is here. Of course, even if you end that, it will land into B. B is already present in the data structure. Therefore, you have got to backtrack. So this choice is incorrect. Now, from C, what is the other way? From C, I can choose x5. x5 is new, and luckily D is also new. So A, B, C, D is totally new. X1, X4, X5 is new. Therefore, this is acceptable. Therefore, I shall further go to the depth. When I go to D, I can use X3. I can use X3, and X3 brings me back to A. A is already present. Therefore, it is backtrack. And then X5. X5 is already present here. Therefore, there must be a backtrack. And if you don't take such an intelligent decision of backtracking here itself, you can still take a later decision, because at a later stage you can find that C is repeated. Therefore, you can backtrack. And then X6 brings you back to B. See, X6 is new in the entire set, but then it brings you back to B. Therefore, you backtrack. And then X8 is new, acceptable. E is also new, acceptable. All right. So E is also new, acceptable. Therefore, you go to the depth. When you go to the depth, maybe E takes you to, if you take X7, X7 seems to be new, but it brings you back to B. Therefore, backtrack. And then X9, it is F. So remove all, delete all these backtrack edges, delete all of them. Then what you get here is a tree. This is the tree. Tree is made up of X1, X4, X5, X8, X9, and it connects A, B, C, D, E, and F. It connects all of them. So this is the backtracked algorithm, or depth first search algorithm to construct a tree. Again, it depends upon the type of scanning that you would do on the data structure. So essentially, it depends upon the choice of the data structure and the sequence in which the edges and vertices appear in the data structure. However, it will not also generate all possible trees. It will generate one. Okay, no problem. So that is the depth first search algorithm or backtracking algorithm. So there must be another way. Obviously, if depth first is possible, then there must be breadth first search also possible. So the breadth first search is, let us start from vertex A. Now you can see that branches are to B, to D, and to C. So branches are to B, to C, and to D, and these are the edges present. Okay. So this is okay, perfectly fine. Now I go to B and try to branch out. Where you look at the diagram, from B you can branch to A, you can branch to C, you can branch to D, you can branch to E, because there are four vertices, 4 edges connecting B. Therefore, there are 4 branches. B, take the branch x1, take the edge x1, then it comes to A, and it is now bound because A is repeated. A is repeated. There are 2 reasons. One, x1 should not repeat. 2, naturally, vertex A should not repeat. x4, see here, nowhere x4 is used, but C is present. Already C is already present here in the first round of branching. Therefore, that should be bound. That should be bound. Now, from B, what is the other choice? I can take x6. No doubt x6 is new, but D is already present. Therefore, that should remain bound. And is there any other choice? B, x7, E. Yes. x7 is not present. E is not present. Yes, this is allowed. This branching is allowed. We can allow this branching. Okay. Now, let us branch out at C. So, the different possible branches at C are taking x2. All right. That is bound because A should not be present again, and more than that, x2 and x2 should not happen. x4 was already considered here, and it was rejected. The same reason this rejects x4 here also, and more than that, B should not get repeated. Okay, it is bound. And x5D, so same reason, I think x5 is not used. Although x5 is not used, D is revisited. So it is bound. So now from D, take x3 not possible, revisit of A not possible, bound, xc bound, and then B, it is bound. Okay, so all branches are bound, and except only this branch which tries to go to the further level. So breadth first search. Okay, in breadth first search, Dr. Javed, please note that it is not DFS, breadth first search. Okay, all right, BFS. Okay, so now it's everything is bound over there. Now only E. From E, what are the branches? E, x7, x8, and x9. So E, x7 bound, x8 bound, and x9, yes, allowed. X9 allowed. So now prune off all these bound edges, all these bound connections, you prune them off. So when you prune them off, what remains is A connecting B, A connecting C, A connecting D, and B connecting E, and E connecting F. This is the spanning tree. This is the spanning tree. So this is obtained by breadth first search. All right. The earlier one was depth first search. Naturally, it gives one tree, not all possible trees. So these are all 5 methods of generating the trees. Okay. All right. Of course, I have not considered the weights here. If you consider the weights, then I will be interested in finding out what is the weight of this graph. Of course, I will be later interested in finding out MST, minimal spanning tree, for which there are 2 very specific algorithms called the Kruskals algorithm and the Prim's algorithm. Okay, so these are the different methods of constructing a tree. Now let us take up one interesting problem arising out of trees. Construct monotonically increasing subsequences in this sequence. 4, 1, 13, 7, 0, 2, 8, 11, 3, some randomly given number, unsorted sequence. But I want you to construct monotonically increasing subsequences. Okay, let us see now. If I start from 4, 1 cannot be included, isn't it? Because it is not monotonically increasing. So remove 1. 13 can definitely be included. 4, 13 can make a sequence. Okay, because 13 is monotonically increasing compared to 4. Now further, when you have decided to include 13, that decision bogs you from including 7, because 7 is less than 13 and I want monotonically increasing subsequence. 0 cannot be included, 2 cannot be included for the same reason, 8 cannot be included for the same reason, 11 cannot be included, 3 cannot be included. Therefore, one monotonically increasing subsequence is 4 and 13. One monotonically increasing. There can be many. For example, if I skip 13 and if I somehow land on 7, 4 to 7, then the next one I can include is 8, which is also monotonically increasing. Then the next one I can include is 11. So 4, 7, 8 and 11 is monotonically increasing, and it seems to be longer than 4 and 13. Like that, I want to find out all monotonically increasing subsequences. Then if I merge all those such subsequences, possibly sorting can be done. Of course, if you get all subsequences and merge, it may not be a good sorting algorithm. You may have to modify that algorithm. All right, you can modify that algorithm, right? So this is the tree diagram that you are going to construct. Either you construct it depth first, like 4, 13, like 4, 7, 8, 11, like 4, 8, 4, 8, 4, 7, 11, 4, 8, 11, 4, 11. So this is depth first, or you go breadth also. You can start from 4, once you start, you can either go to 4, or go to 1, or go to 13, or go to 7, or go to 0, or go to 8, 2, or go to 8, or go to 11, or go to 3. And then there is one knowledge that 13 is obtained, and that is a end point, because after that there is no monotonically increasing possibility at all. Similarly, 11 is an end, 3 is an end, 11 is a end, 3 is a end, 13 is a end. Okay, all right. Now I just wanted to give you some interesting advanced algorithms, interesting automatic machine learning could be possible. For example, assume that you have done a depth first. Having done a depth first, see here, 4, 7, 8, 11 is already obtained in the depth first, right? Okay. Now when you come over here to 7, you should know that already the balloons connecting 7 are known to you. 7, 8, 11, this is known. So you should not reinvent this. Machine should not reinvent this. Cut this, attach it here. Straight away that should become the answer. Cut this and attach it here. So if the depth first is done, after 2, what are the connectivities are already known. And here after 2, what are the connectivities? You should not re-explore. You just cut this and connect it here. That's all it should happen. That's the intelligent algorithm. Again, from 2 here, already you have got the answer. So machine should automatically tell that everything is done. You need not redo it. The 2 things are possible. There is a specific knowledge that can be learned, and machine can propagate that knowledge in the depth first sequence, or there is another specific language which is generated when you go breadth first. The specific language, the specific knowledge which is generated when you go breadth first is 13 is a termination, 11 is a termination, 3 is a termination. This is a knowledge. So the moment you come to 13, you should know automatically that it is a termination. The moment you reach 11, you should know automatically that it is a termination. That is the knowledge. Is it all right? So whatever branch, there is a branching knowledge or there is a depth knowledge. Okay, so both of them could be useful in solving the problem, and naturally it is up to you to display whatever are the original thinking and whatever would be the advanced method of learning that could be possible in constructing a tree should be illustrated by you. Now you look at the same problem. Let us go depth-wise. All right, let us go depth-wise. So here, and do it a little more intelligently. So maybe I'm interested in monotonically increasing subsequence. Okay, so 4, and then monotonically increasing is 13, and I shall try the remaining, and I definitely see that none of them are increasing. Therefore, one subset is 4 and 13, isn't it? One subset is 4 and 13. Remove that in the list. Remove that. Okay, don't retain them, remove. So now what removes is 13 is removed, 4 is removed. Again, try monotonically increasing sequence. 1, 7, it starts from 1 now, because the 4 is gone. 1, 7, 0 cannot be included, 2 cannot be included. Yes, 8 can be included. Yes, 11 can be included, 3 cannot be included. So another sequence, increasing sequence is 1, 7, 8 and 11. So write it down. 1, 7, 8 and 11. Remember, what is the first subset? 4 and 13. What is the second subset? 1, 7, 8 and 11. Remove that. When you remove it, 4 is removed, 1 is removed, 13 is removed, 0 is removed, 8 is removed, 11 is removed. What is remaining is 0, 2, 3. 0, 2, and 3. And luckily 0, 2, 3 is also an increasing subsequence, right? So there are only 3 subsets with increasing subsequences. One is 4, 13, another is 1, 7, 8, 11, and another is 0, 2, 3. Now do the merging of all these 3, it will become sorting, right? So sorting is done. Implement this algorithm for sorting, okay, which is depth first search of all monotonically increasing mutually exclusive subsets, whereas this shows overlapping subsets. This diagram creates overlapping subsets. The algorithm which just now I explained will give you non-overlapping subsets. All right. Now I have described depth first search. You definitely do breadth first search. Let us see by what is the knowledge, what type of subsets you would generate if you employ breadth first search, and then you surely can do sorting algorithm. You can realize the sorting. Okay, good. Okay, so now distance between two vertices in a tree. See, what are the distance in a graph? In a graph between the two vertices, there can be more than one path, and the shortest path is done which contains a minimum number of edges, theoretically. Practically, shortest path is that whose weight of edges between those two vertices, sum of the edges, sum of the weights of the edges should be minimum. That is practical. But here in a tree, there is one and only one path between any two vertices. Therefore, the path length between the two vertices is the distance between the two vertices in a tree, because there is only one path. That is the minimum path length in a graph. Okay. Okay. On the other hand, minimum path length in a graph is different, and in a tree it is just the path length between the two vertices. When I speak about distances, distance between the two vertices u and v is said to be a metric. When do we tell that a function is a metric? The function should satisfy the following 3 properties. One property is the non-negativity. The function should be, the value of the function should be greater than or equal to 0. The distance between u and v is always greater than or equal to 0. It can be equal to 0 provided both are same vertices. If the distance from u to u is 0, the distance from v to v is 0. The distance from any other vertex to any other vertex is definitely more than 0. So non-negativity is satisfied. Symmetry, function xy should be equal to function yx. So in case of a tree, the distance between u and v is same as distance between v and u. Not in a graph. Note that. In a graph, the distance from u to v need not be same as v to u. Okay. And this is another triangular inequality. The function, the value of the function fxy is always less than or equal to the value of the function fxw, some other vertex w, and fwy. So this is a triangular inequality. Naturally, it is very simple and a very interesting philosophy. Fxy is a direct communication, between you and your friend, and the same communication happens through some intermediate friend w. Then there may be a noise added to that. Therefore, any communication through an intermediate friend will definitely be, there is every possibility that it will be greater than the direct communication. Of course, if the W does not add any noise, then it may be equal to fxy, but certainly it cannot be less than fxy, right? So the direct communication, the direct value is always less than the indirect value, or in the best case, it can be equal to the indirect communication. So DUV is a metric. So if a function has got to be a metric, it has got to satisfy all these conditions, and then the distance between two vertices in a tree is always a metric. Okay, like that. Now we shall introduce one more interesting component called eccentricity of a vertex. Eccentricity of a vertex. You know that man is defined to be a friend, provided he maintains good friendship with everybody. If man does not maintain very good friendship, and if man or woman is not approachable at all, if he does not like to be approached by anybody, we call such a person as an eccentric person, isn't it? Eccentric person. Who is the class representative? Class representative is that person who is reachable to every other person in a class. Whereas eccentric person who maintains the longest, who maintains the biggest distance, the largest distance, may not be the right choice. So let us define what is eccentricity of a vertex. Eccentricity of a vertex is, of any vertex V, is its distance, it is not distance of that vertex V from the farthest vertex. Okay, so in a graph, you visualize a graph, you consider a vertex, and to that vertex there is one vertex which is at the farthest point. What is the distance between this vertex and the vertex which is placed farthest to this vertex? That is what is the eccentricity of the vertex. Is that clear? So eccentricity of any vertex is the distance that it maintains from the vertex which is placed farthest to it, which is far away from it, which is at the most far away point from it. So mathematically, eccentricity of a vertex, you consider all distances from that vertex to all other vertices in the graph, and the maximum of all of them is the eccentricity of the vertex. So it is you list all the distances of the vertex that the vertex makes with all other vertices Vj's, and the one which is maximum is the eccentricity of the vertex. Okay, all right. So a vertex with minimum eccentricity, a vertex is the minimum eccentricity, is the center of the tree. So a person with minimum eccentricity is the excellent class representative. A vertex with minimum eccentricity is the center of the tree. So if two vertices are centers, then they are adjacent. Let us see a simple example. What is the eccentricity of this vertex? Eccentricity of this vertex which I am marking is 2, because the farthest vertex for this is either this or this. Therefore, eccentricity is 2. Okay. What is the eccentricity of this vertex? The farthest vertex is this. The farthest vertex is this. The farthest vertex is this, and eccentricity is 1. And what is the eccentricity of this vertex? Eccentricity of this vertex is 2, because the farthest vertex is this, or the farthest vertex is this. So eccentricity is 2. So 2, 2, 2, and 1. And this is the vertex with minimum eccentricity. Therefore, this is the center of the tree. Center of the tree. Is it okay? Now, in this graph, the eccentricity of this vertex is 3. 3. See, 1, 2, 3. That is the farthest vertex. Eccentricity of this vertex is also 3. Eccentricity of this vertex is 3. Eccentricity of this vertex is 3. Eccentricity of this vertex is 2. Eccentricity of this vertex is 2. All right. And there are two centers, and they are both of them are adjacent. The moment I introduce the idea of the center, surely idea of the center gives a picture of a circular representation of the tree. All right. And the radius of the tree is the eccentricity of the center. Radius of the tree is the eccentricity of the center. Is it all right? What is the diameter of the tree? The largest eccentricity present in the tree is the diameter of the tree. Okay. So it gives you to picturize it as a circle or as a graphics representation. Okay. All right. So now let us see what can be the algorithms to find out the center of the tree. Now, what is the approximate center of a graph? The approximate center of the graph is convert a graph into a tree and find out the tree center. The tree center is the approximate center of the graph. So now to find out the tree center, one algorithm is tabulate all eccentricities and choose that vertex whose eccentricity is minimum. Another is you just peel off all these pendant vertices. Peel, just remove the pendant vertices. Then you are left with only one vertex, which should be the center. You keep on removing the pendant vertices. So there are two algorithms. Okay. Number one, keep removing the pendant vertices repeatedly till center is reached. Repeatedly. So where are you going to peel off, remove these pendant vertices? In the matrix, in the A matrix or in the X matrix. So you start with A matrix, identify all pendant vertices in the A matrix, remove them. When you remove them, A matrix gets reduced. Again, in the A matrix, you can find new pendant vertices. Again, remove them. Again, you reduce the A matrix. Like that, you keep on repeatedly doing till you are left with only one center or with the two vertices which should be adjacent. Okay, that becomes the center of the tree. So that is the algorithm. So there are two algorithms to find the eccentricity, the center of a tree. One by tabulating the eccentricity, another by peeling off the pendant vertices. Okay. Now you have got to prove why peeling of pendant vertices shall not disturb the location of the center. That you have got to prove. Okay, you can prove that. So E of the center, eccentricity of the center is the radius, maximum eccentricity is the diameter, which just now I have told you now. So that you have got to do it starting from A matrix or starting from X matrix, okay, of the tree. Okay, all right. Now let's see a very specific tree called rooted tree, the binary tree, which you might have already studied in your data structure classes, and quite often you have studied in algorithms classes also. So in a full binary tree, the depth of the binary tree, which is normally called height of the binary tree, is log n plus 1 to base 2 minus 1. How is that? Okay. So the number of pendant vertices in a full binary tree, is n plus 1 by 2. Number of pendant vertices is n plus 1. Remember, the minimum number of pendant vertices should be 2. The maximum number of pendant vertices can be n minus 1. But in a special binary tree, the rooted binary tree, it has got to be n plus 1 by 2. Let us see what is a full binary tree. This is the full binary tree, you know that. And you can count that the number of pendant vertices is total number of vertices plus 1 by 2. All right. So this is the full binary tree. Of course, this full binary tree has many levels. Here there are 2 to the power 0 number of vertices in level 0, and in level 1 2 to the power 1 number of vertices, in level 2 2 to the power 2, in level 3 2 to the power 3. Like that, the total number of vertices is 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3, like that, plus 2 to the power last level, let us say it is L, should be equal to total number of vertices n in a full binary tree. All right. So now if it is not a full binary tree, highly sparse binary tree could be a skew or a linear tree like this, This gives the maximum height, and the maximum height is n plus 1 by 2. Whereas the minimum height is log n plus 1 to base 2 minus 1, which we have got to derive. Quite easy to derive, that's not a big issue. Now let's see this particular tree. In a full binary tree, there is only one vertex of degree 2. How many? Only one vertex of degree 2. And let us assume that there are p pendant vertices, and each pendant vertex has a degree 1 only. And all these are internal vertices. Okay. And all these internal vertices are of degree 3. You can see these are all degree 3. How many degree 3 vertices are there? Minus a root minus the p. So total number is n minus p and minus 1. N minus p minus 1 will be the total number of trivalent vertices. Okay. So I use this knowledge and write down the equation. There is only one vertex of degree 2. So total degree contributed by that is 1 into 2. And let there be p number of vertices, pendant vertices, and each one of degree 1. So p into 1. And therefore the remaining vertices is n minus p minus 1. And they are of degree 3. So this is degree 2. This is p into 1. This is n minus p minus 1 into 3. Sum of all the degrees is equal to twice the number of edges. Sum of all the degrees is this. It is equal to twice the number of edges, 2 into n minus 1, because the number of edges in a tree is n minus 1. So only unknown in this equation is p. Solve for p, you will get p is equal to n plus 1 by 2. Is it all right? Solve for P. You will get P equal to n plus 1 by 2. Where is P? P is in the last level. How many vertices are there in the last level? 2 to the power L. Therefore, 2 to the power L is equal to n plus 1 by 2. Is it all right? 2 to the power L is equal to n plus 1 by 2. And now, since 2 to the power L is equal to n plus 1 by 2, then take logarithm on both the side and simplify. You will get that expression log n plus 1 to base 2 minus 1. That's all. Very simple. That is the last level. That is the depth. Okay. Divisive procedure. Now, to traverse from a vertex Vi, I will just go back. I will ask a question. I want you to traverse, say, let us say from this vertex to this vertex. From this vertex to this vertex in this full binary tree. How do you traverse? So you know that you cannot traverse downwards because you have got to go here. You cannot traverse downwards. You have got to traverse upwards. And this is the return point. And after that, you have got to go in this direction. All right. So let us say I want to traverse from here to here. I want to traverse from here to here. See the arrow on my screen. I want to traverse from here to here. If I want to traverse from here to here, I know that I cannot traverse downwards. I cannot traverse downwards. I have to traverse upwards. Why do I know? Because the picture is available to me and my eyes are seeing. This is a vision algorithm. Whereas this is the same vision algorithm which you have got to simulate on a matrix. Okay. How do you know that you have got to move upwards? You have got to move upwards. And should I still move upwards up to this point? No. You should stop here. How do you know? How will you get to know that? And then start moving downwards. Okay. From here, you start moving downwards. I should not move up to this point. I should move here. This is the returning point. Okay. Now, I want to move from here, let us say to here. So I have to move upwards and then downwards. Okay. Let us say I want to move from here to here. All that I have to do is only move downwards. Okay. How do I know all these things? So if I give two vertices, two vertices, Vi and Vj, you should find out the traversal, automatic traversal in a full binary tree, for that matter, in any tree whose data structure is available. All right. Okay. Okay, that's that. This is the question which I have given here. All right.